How fun is that going to be? We talked about area, we talked about arc length. We're going to go full 3D with this lesson. So to get going, we're going to be building some three-dimensional solids and calculating the volumes of those three-dimensional solids. And we're going to do that by looking at the cross sections of the solid. So you need to have like good spatial awareness of what's going on. You need to remember your geometry formulas. That could definitely help out. You need, or you don't need 3D glasses. That's me being goofy. All right, so if we think about how to find the volume of some old geometry things like a cylinder and a rectangular prism, whatnot, right? You probably recall these formulas. Volume of a cylinder is pi r squared times the height. Volume of a cereal box is the length times the height times the width. If we had a toilet paper roll, right, to find the volume of the paper, you'd have to take a big cylinder and subtract a small cylinder. So you would have basically two cylinders, one subtracted from the other, which you could simplify the formulas so they look like that. Or that cool eraser you had in fifth grade that looked like a star. You remember that one? Yeah, I had that one too. But if you could find the volume of that if you knew how to find the area of the star and multiply by the height. And that's what we got in geometry, that the volume of any prism was just cap B times H, just the area of the base multiplied by the height. And maybe it really didn't give it a second thought, but why? Why is that true? I mean, ready? Hiya! We're going to hiya those things and look at their cross sections. If you look at the cross section of any one of those prisms, you get a circle for a cylinder. You get the square or the whatever the base shape looks like. You get this donut shape in a toilet paper roll, and you get the star anywhere you cut parallel to the base. You get a congruent figure to the base. And that's pretty boring when you think about it, right? The reason that we have the volume of any prism is just the area of the base times the height. Is so we get this two-dimensional area formula multiplied by a one-dimensional height, because they're all of the cross sections are all the same throughout the entire prism. And we just have this three-dimensional quantity then. We have 2 dimensions times 1 dimension is 3 dimensions. But what happens when the cross sections are not the same size? What if they're similar, right? We're not going to get so crazy, which maybe we could, where the cross sections change shape. But here we're just going to talk about what happens when they change size. What happens when they're similar throughout? So like a vase, right? In a vase, if you cut it somewhere, you're going to get a circle. Now that circle could be small, it could be big. It's different sizes. So how would we find the volume in that case? Because it's kind of like a cylinder, but it's kind of not at the same time. Well, this looks like a job for dun, 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 a definite integral. That's right. You know it's coming. But how is it coming? Trip down memory lane for you. Now, we found the value of a definite integral by adding up infinitely many, infinitely thin rectangles that fit inside of a region, right? So we took the height, which was some f of c sub I. We took the width, which was some delta x sub I. We multiplied those two together. We added it up. We made the number of subintervals go to infinity, and that limit of a sum turned into the definite integral. The whole point of a definite integral was that infinitely thin and infinitely many little shapes that, or the rectangles that fit inside of that region. So this picture, that picture could say it all. It's kind of tiny, but if you look over there, it's got all the pieces, right? It's got all the. I didn't draw them all. I didn't have time to draw infinitely many rectangles. Gave me a break. But you can see that there would be infinitely many. The subintervals all sliced up there, becoming infinitely small, size of 0. But it's this idea that we have infinitely many and infinitely thin that is going to continue here when we think about volume. We've already seen the idea with area and with length, the infinitely many, infinitely tiny idea. We know it's going to turn into a definite integral. So what we want to do is we want to add up these little slices, almost like a loaf of bread, right? That is just sliced infinitely thin into infinitely many pieces. And we want to calculate the volume of each little bread slice. We would see that each little bread slice is a prism with whatever shape as the base and a little tiny, infinitely small height. So the volume of the slice would just be the area of the shape or area of the base multiplied by the tiny little thickness, which is going to be some delta x or delta y, depending on the direction of how you stack your solid. Now, your solid could be stacked perpendicular to the x-axis, which means just lay a loaf of bread on the counter, right? The width of each slice is a small change in x. But if you maybe put the bread on its end like this, and you saw those slices perpendicular to, say, a y-axis scenario, each of the thicknesses is a small change in y, or delta y. Those are going to be you can see that height, that thickness, is some little tiny delta x or y. So we want to find the volume of each slice, add the volumes together, make the thickness go to 0, add up the infinitely many, and presto, we got ourselves a definite integral. Oh my gosh. Okay, so here comes a little picture. Here is a really weird looking loaf of bread, but each little tiny slice, each little bread slice, each is a prism, where the thickness is really tiny, a change in x, and then whatever that base area, geometry, shape is, we could calculate the volume of each prism if we knew how to come up with the area of that cross-sectional shape. So here is the idea. We're going to add up the area of the base times the delta x, and that's going to turn into the definite integral. So the definite integral from a to b of this area formula times delta x should be dx there. So the idea here is that we want to come up with an area formula for a cross-section shape based on some of the functions that are in play. And you'll see a little bit better what I'm talking about as I continue. So we definitely want to draw. We definitely need to be able to think through this spatially. It's hard to draw three-dimensional things on a screen or on paper. So this is really kind of depending on your ability to visualize 3 dimensions. I can't do that for you, but I can help you think through it as clearly as I possibly can. Okay, so let's see the big idea here. The big idea is we want to integrate from A to B the area formula in terms of x of the cross section with respect to x, and that's if the slices are perpendicular to the x-axis. And if we're perpendicular to the y-axis, everything just flips over to terms of y. We need to come up with the area of the cross-section in terms of y this time with respect to y. So the integral is fairly simple, and I'm going to show you a few examples here to help get the ball rolling a little bit. So we're going to start with the area formula. We're not going to start with calculus here. We're going to start with geometry. You're going to be told what the cross-sectional shape is. Semicircle, triangle, square, rectangle, what have you. You're going to start with the area formula for that shape. And then you're going to substitute in for whatever distance might be part of that area formula. The length, top minus bottom or right minus left, is back. Top minus bottom, right minus left. Those are ways to represent distances, vertical distances, top minus bottom, horizontal distances, right minus left. And we're going to substitute that into the appropriate spot in our geometry formulas. Okay, so it's important to know the geometry formulas. I mean, we're talking squares and rectangles and triangles here, so it's not like you gotta go back and dig through your geometry textbook in order to figure some of this stuff out. Okay, let's look at an example. So here is a region. The region bounded by the graphs of 2 plus sine x and this quadratic, x squared minus 2x plus 2. Here's what it looks like. All right, so that is going to be the base of a region. That's like our bread pan. Okay, so that's what we're going to be building off of. So we're going to slice this thing perpendicular to the x-axis. So you can see those slices there. So you can see that each width of the slice is a delta x. But what we're going to do is we're going to build off of that a rectangle whose height is half of whatever that base length is. Okay, I'm going to do my best here to show you what this might look like, a three-dimensional rendering on a two-dimensional screen. Okay, so imagine dropping the region flat, and then each one of those slices, now a rectangle protrudes from that flat planar region. Slide out one of the pieces, and that individual slice is going to be a rectangular prism. That rectangular prism has a dx thickness. It's got a base that is in the xy plane, and it's got a height that is protruding from the xy plane that is half of whatever that base length is. Okay, so the idea here is we want to start with the area of the cross section. The area of the rectangle is the base times the height. Well, the length of the base is that length in the plane, the distance between the two functions, right? So the distance between f and g, think top minus bottom, the base length is f of x minus g of x. Well, the height then is half of that length, so half of the quantity f of x minus g of x. Therefore, the area of the rectangle can be written as base times height, where we've got an expression for each one of those, and we can simplify that to 1/2 times the quantity f of x minus g of x squared. So that would give me a formula to find the volume of one of the slices. We want all of the slices, infinitely many, and that's just going to turn into the definite integral. So it's just going to be the definite integral. Here it is. Oh my gosh, where'd it go? The definite integral. Oh my gosh. Oh, I'm flying all over the place. The definite integral from 0 to 2.3, which represent the intersections, by the way, which I didn't say. The definite integral from 0 to 2.317 of that area formula that we created, 1/2 of f minus g squared with respect to x. Boom, there it is. That is going to give us the volume of that solid. So let's see maybe a different shape. Okay, same base. All right, same base. F is on top, G is on bottom. We're going to cut perpendicular to the x-axis. We're going to drop it flat, but this time we're going to have semicircles come out of the page. Okay, so semicircles are going to be building off of that region. Here is a rendering of what that might look like. So how do we find the volume? Well, we got to start with the area of the cross section, which is just pi times the radius squared, cut in half. Pi times the radius squared cut in half. I'm a goofball. So in my next video, I'm going to fix all this. All right. So check out the next video. I'm going to fix this and be back.